Okay, Assalamualaikum warahmatullahi wabarakatuh. Right now we are dealing with chapter 4.7 and 4.8. If you look at the slide, it's basically the name of chapter 4.7-4.8, right? And in this slide we will cover the simplification of force and coupled system and their further simplification. Basically, this is to simplify the drawing of multiple of forces and coupled moment, etc., into a simplified version, right? So that's basically the idea. In terms of application, you should just read the slides basically. But if we want to design something, right, and we want to design the support here, so if you have force, multiple moment, etc., so sometimes what I want is just at this point here that I need to support, what is just the equivalent of all of this, right? So that I can design the support there, right? So the idea can be like that, right? So we do not want to know all these forces, etc. We just want to know, okay, equivalent for this one, so that I can design to sustain that one, right? So that's the idea. Alright, so simplification of force and coupled system. When a number of forces and coupled movement are acting on the body, it is easier to understand their overall effect on the body if they are combined into a single force and coupled moment having the same external effect. So basically, when you simplify, the new drawing, which is simplified, actually have the same exact effect of the original all forces and coupled moment, right? So that's the idea, because we just want to simplify the force and the drawing so that we can measure easily, but the effect is actually the same, right? Two force and coupled system are called equivalent system, and since they have the same external effect, okay, right? So that's from the slide. So imagine this scenario, right? If we have let's say, right, just like in this slide, right? Let's say we have this force and we have this force, right? This is the same, right? Basically, we are drawing the same, right? Now, if I am to add force here and force here, do I actually change anything in terms of the effect? If I add to the right and to the left, is it changing anything to the structure? No, right? Because this actually cancel each other and it doesn't affect anything, right? Can I then cancel this one and this one? Okay, that's the next step. Can you cancel this force and this force? Can you? It can, right? Because it's one here and one here. It basically cancel each other. So effectively, when you cancel each other, it becomes like that. Meaning, this is exactly the same as this in terms of the effect, right? So this one you can call it, I think it will call the sliding vector, because this force here, if you just slide along this line, it doesn't have any change on terms of the effect, external effect. So no problem there. Let's imagine something else. Okay, similar beam. So similar original force, but if you have something like this, right? Okay, imagine this. If I add this force and this force, do I actually change anything to the structure? No, right? Because you add basically zero force, because this simply cancel with this one, right? Now, if you look at this one, can I cancel this with this one? Because one goes up and one goes down. Can I cancel them? If yes, why? If no, why not? Now, if you notice from what we have just learned in the previous recording, these two are a couple, right? Because they are having the same magnitude and opposite direction. So this is M, this M. This couple, right? So couple, of course, the net effect in terms of the force, as we have discussed in the previous lecture, is zero, right? And it's obviously zero, right? One goes up and down. But it does have the tendency for rotation, right? In this case, the tendency for rotation is counterclockwise between this and this, right? It is counterclockwise, right? So if you want to erase and replace, you have to replace with the same effect, right? So if I have to erase this one, the same effect in terms of forces obviously is 0, so no problem. But in terms of the rotation that the couple is producing, you have to redraw it here, basically something like this, right? And this M is just simply the couple is the force times the distance there, right? For example. Alright, so you can see that these two are equivalent, right? Because side by side, what we do never change the external effect. So the effect of this is the same as this one, right? So you can see that if I want this force to be here, which is here, I have to introduce moment because that will be the accurate representation of effect on the structure, right? So that's the idea, right? But of course this is a free vector. This M is a free vector because, as we have discussed, couple moment about any point will always be the same the moment, and if you push the couple moment anywhere, it will always be the same as well. So it doesn't matter, right? So this one is basically a free vector that we have discussed earlier, right? So if you draw it here or here, it's basically have the same external effect. Right? Why are we talking about this one? Because this is some of the concept that is needed when you want to simplify the force, right? What we mean by simplify is basically if you have something and then you have whatever and whatever, and in the end you just want to have one force and one moment there. So basically you can transfer everything there, right? But for each transfer, it does actually introduce the moment, the couple moment, so that the net effect is still the same, right? If you just shift the force without compensating for the moment, actually the net effect is not the same, right? Because you are actually, like we have illustrated here, you are actually cancelling a couple, right? So you have to introduce the moment, which basically have the couple effect, right? So that's the idea. Alright. And if you can notice, this is how to see why in the slide you suddenly have that equation, right? Basically, this process here, right? This F is still the F, right? So when you shift any of this F, it goes here, it's still that F. This one goes down, it's still that F, right? So in the end, this Fr, the resultant force, is just simply the summation of all forces, because the forces never change, right? When this go here, it's still that same F. The only new thing is the moment, right? So similarly here, so this F goes here, it's still that same F, the same F, and the same F. So in the end, this Fr is just simply summation of F, and this is only true if you have in vector form, obviously. So in terms of Yjk, if you add M up together, it will give you the same thing, right? In scalar, it will be different, right? Because scalar, you cannot add if the direction is not the same. And in terms of moment, you can see that the equation, because this M is basically from this F times this D, right? Meaning that if this is D, so M equals to F times D. Right? Why is that? Because if I just to redraw the original couple, right, which we erase and replace by this one, it is actually that force multiplied by the distance d, right? So it's straightforward like that. Okay, so that's why you end up with that equation where I say moment R is just summation of all moment, or in the slide they actually just split this into two, where you have summation of moment from couple moment plus summation of moment about a certain point, right? About the force about this point basically, right? So that's how this is understood from or derived or something, right? So if you understand, even if you do not memorize, you understand what's going on, and it's basically just the resultant force is just summation of all forces in vector form. In scalar form, you have to use or resolve x and y, add the component x and y, and then you get the resultant back with square root, right? Okay, so that's the idea. I think we have the example. Okay, further simplification. So there's no example yet, but it's add up another theory, right? Now, the idea is simply like this. Because in the slide, it draw in terms of 3D examples to illustrate what is simplification and further simplification. I'll just illustrate in 2D, right? So if originally I have forces here, 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 and here, right? And then when you simplify, meaning that if the question says we need to find the resultant or no, the equivalent force and couple moment system at this point O, meaning that it will be something like FR here and then MR there. The direction I'm not sure, this is just assumption or example, right? So how to get this FR? In this case, if everything is vertical, horizontal, right? It's simply just summation of all the force, right? So let's say this is 10 minus 5 plus 10 plus minus 5, you get whatever value if it's always in the same direction, right? What about MR? MR is just summation of RD, right? This because we are using scale, right? It's basically summation of moment, right? In vector form, for example, right? So for example about this one, so this one will be rotating clockwise f times distance, this one counterclockwise f times distance, this clockwise f times distance, etc. So that is individually you can calculate the moment about the point, about this point or this point, and then this is the summation, right? All of that, because the effect is the same, so it's just the summation. So that's the idea. But this is not all, because later when you say further simplification, is what it means is instead of FR and MR, I just want FR. I want it further simplified. So basically you can just shift it back to somewhere where this distance will actually compensate for the rotation. Okay, in this case it will not be logical, right? Because logically it will be the other way around. Okay, so let's make it like that, right? Okay, so how do you know this distance D, let's say, right? Is there any D before? Right, let's say this is distance D, and we need to find that. So that's normally what is being asked if you do further simplification, right? So because further simplification, you further simplify from 2, which is force and moment, into just force, right? So you need the distance, because this is distance that produces the moment clockwise, which equal to this clockwise, right? So in that case, this moment here, MR is just basically it's MR should equal to FR times distance, right? Because the effect is the same. In terms of force, FR is FR. In terms of moment, this moment clockwise should be the same as this moment clockwise, right? The effect is the same. So you can calculate if you need to, right? But the idea is like that. So if you see the example, let's start with this 2D example. Something like that. And then you have force here, and then you have force here, and then you have force here, right? So okay, let's put the value. This is 200 kilonewton, this is 100 kilonewton with the angle of 3, 4, 5, like that, I believe. This is 50 kilonewton with the angle of 30 degrees. So what to do? If the question says find the equivalent resultant force and couple moment acting at A, and then the equivalent single force location measured from A. So this question, there's example 1, the question actually have two parts. One part is what is point A? This is point A. Okay, so this is point A, and this is 3 meter, 3 meter. Right? So what the question 1 is basically just, first step is, what is the resultant force here and what is the moment there? Right? Is it still in the frame? Yes. So that's basically the simplification, right? So what is the force and couple moment equivalent, right? When you simplify, right? So make sure you also are familiar with the wording that it uses. Here it says, find the equivalent resultant force and couple moment. So you should understand, equivalent force and couple moment, that is what it means. Alright. So what to do? Where you have this is FR and MR. Of course, I'm assuming the direction, I do not know. Now, so what you do is, basically if you have 2D, you have to resolve this, for example this one and this one, this one and this one, and then you just get the resultant there, right? So, in terms of the x component, summation of all fx, no x component, this one is, we get 100, 3/5, and then this one is plus 50 sine 30. That's the total of x component. What about summation of fy? This is obviously to the right. Fy is upwards. So this will be 200, and then this one is minus 104/5, and then this is plus 50 cos 30. Right, so you have that one. Regardless of the value, whatever the value that you have, for example, this one tend to be positive, is it? Let's assume this is positive, and this is also positive, meaning that fx or summation of fx and summation of fy in this direction. If that is the case, then fr is indeed here with a theta there. Right, so your answer should carry all of those information. Right, and I believe you know how to calculate this one already from whatever given data there. Right, what about mr? So the result of moment and the moment from each individual force should be the same, right? So basically, for mr, is simply just summation of f times d. Right. Let's take counterclockwise positive, because I do not know the answer, so let's take counterclockwise positive. So this one about point A is counterclockwise, right? So 200 times 3. And then this one, the horizontal component doesn't have any moment, so the vertical one is clockwise, so minus 100 4/5, and then that one, the vertical one also that we want, so that is plus 50 cos 30 degrees. Right, so this is the resultant of moment, so you get whatever value there. Right, so that's how you solve for scalar operation. It's not difficult, it's just you know what to do. Right, but this is not yet the end of the question, right? Because this is only the first part, which is find the equivalent resultant force and couple moment acting at A. So we have this one. Now the question says next, find the equivalent single force location from measured from A, meaning that next is you shift this FR here, and what is this D that will actually nullify this one, meaning that all the effect of rotation is already embedded in this one with its own location from this point, right? So yeah, hopefully you can understand what to do, right? So how to solve this one? So basically this moment here, which is the original moment, and this moment about this point, which is, it should be equal, right? So this moment should equal to FR y, which is the y component, and then times d, something like that, right? Because I'm not showing the detailed calculation because of the number. I don't have the calculator, and I do not want to spend using my calculator in this slide, in this recording. Right, so hopefully you can try and see what you get. Right, and so you have two parts of question. First, FR and MR, and then what is the distance to further simplify. Okay, and you can see the answer there. Obviously, as I mentioned, even though the question never asks for theta, but because you get the resultant where you have a theta, so you have to specify that theta somewhere or in one way or another, so that you get the marks also. Right. So in this example, there's a slab there, and right. So let's attempt on this one. It seems easy, and it should be easy, but it may take some time. And given that it is already 2 AM, I'm quite sleepy, unfortunately, but we'll go through. Hopefully, you will benefit from this. Right. So basically, you have the axis there, and then basically you have something like this, right? And then you have three forces. So one force is here, one force is here, one force is here. Is my drawing accurate? Okay, it's not accurate because it's long doing this way, but you can refer to the slide and to see the actual diagram, but I'm just using this one, and the ratio might be off, but hopefully you can still follow, right? So basically this is 400 Newton, 500 Newton, 100 Newton, 3 meter to this point, 4 meter in total, 4 meter in total here also. So my drawing is not according to scale, unfortunately, right? But hopefully it still can follow. The question says the slab is subjected to 3 parallel forces. So you have the forces, 3 parallel forces, all going vertical. Find the equivalent resultant force and couple moment at origin O. So that's the first part. Also find the location XY of single equivalent resultant force. So this question can actually be solved by vector or scalar, right? Which one should you first? Right. So the idea is like this. So what we want is basically, in the end, the first step is to shift everything to this point, right? For example, like this and something like that, right? So FR, MR. So that's basically the idea of what we need to find. What is FR and FR? That's the first step. And of course the second step is, what is this location, right? So when this is FR, so what is this X, Y coordinate? That will be the further simplification, where this will give you the effect of this one. Right, so first step first, how to get FR. In this case, it's quite obvious, quite easy, so because FR is just summation of all forces going down. If we take down as positive, should we take down as positive? Okay, let's take up as positive, right? So that we use normal conversion. So in this case, we have 100 minus 400 minus 500. So you get minus 800 Newton downwards, right? Oh, what's that? Meaning, if you consider upwards as positive, so downward will negative means downward, straightforward, right? So this one will be that value there. And then what about MR? Right? So it's basically the summation of all moment, right? Of course, this one you do not need to use vector, because if you use vector, it's straightforward as well, right? But for MR, if you want to use vector, so let's say we use vector, right? It will be summation of R cross F. Right? Meaning that r cross f for this one plus r cross f for this one plus r cross f for this one will be the moment, the resultant moment. Right. So if I do that, so for this one, and we take about the origin, so we'll have j, k, r will be, okay, this axis is, this is x, y, z axis, right? So this one will be 3i minus plus 0j plus 0k. Let's stick with that, right? And then the force is 0, 0, 100, positive. So that is settled for this one. What about this one? Minus 400, right? So plus, so I, j, k. So the distance here is just 4 in y axis, so 0, 4, 0. And that is just downward, so 0, 0, minus 400. Right? And as you can see this value here, because everything is vertical, etc., it will be easy because the solution of this one will be easy because there's a lot of zero. And you have this one to take care of, so you have another one, so plus I, j, k. Is it still in the frame or not? I, j, k. Is this in the frame? Yes. Right, so r will be, of course, 4 and 4. So it's basically 4, 4, 0, and then 0, 0 minus 500. Right, so in the end, basically you'll get in terms of ijk. For example here, I is 0 minus 0, right? And then minus j. Okay, so I is 0 minus 0. Minus j is 300 minus 0, right? And then plus k, 0 minus 0. Right. In this case, plus I, minus 1600 minus 0, minus j, 0 minus 0, plus k, 0 minus 0. Right. Here, plus I will be minus, minus 2000 minus 0, minus j, minus 2000 minus 0, plus k, 0 minus 0. From here, you will see that for I you get minus 1600 minus 20, so minus 3600I, okay, and then for J you get minus 300 minus plus 2000, so plus 1700J, of course plus 0K, right? So that's basically MR in terms of vector. Right, does it say in terms of vector scalar? Right, so in terms of, okay, if you need in terms of scalar, then you have to square root it, right? So that's the magnitude of the moment. Right, but this is in terms of vector consistent vector form. Right. Now also find the location of xy for a single. So how to move here? Right. So basically the concept is, this is the moment result. This one, if you do r cross f, for example, the moment should be the same. So meaning that here, if you do r cross f, because mr vector here should be the same as r cross f r here, right? This r basically, right? So mr is basically that one, right? Minus 3600I plus 1700J plus 0K equal to r. R is what in this case? If you have x and y component axis, so it's just xi plus yg plus 0K, right? And then you cross with FR, which is this one, which is in vector form, is minus 800 downwards, right? So minus 800 K. Right. So if you do the cross here, if I bring it, is there any place? So let me bring it here. Right? So if you bring it here in the cross, so you'll get I J K. Is it in the frame? Yes. So X Y 0 0 0 minus 800. Right? This is R cross F for this one, for this diagram, right? So if you will get I minus 800 Y minus 0 minus J minus 800 X minus 0, and then plus K 0 minus 0, right? So if you have already this and you say that this one should equal to MR, so you already have the values here, right? So from here, for I or X component, basically it's 800 minus 800 Y should equal to minus 3600. So Y you can able to calculate. Similarly for J component, right? So for J component, so here is minus minus becomes 800 X should equal to 1700. So X should be equal to something. Once you get that, again check what you need. Okay, this is the coordinate. So X, Y coordinate is obtained from there. Right? Hopefully you follow the steps. It's not difficult, but that. You can also try this with scalar, right? But if you use scalar, obviously you do not have IJK or R cross F. You basically have to define what is the rotation, plus and minus, etc. And then you will see that the answer will exactly be the same. So not a problem. So please try if you want to try in scalar. And if you do not get the answer or have any problem, do consult me in the class. Alright, do you have any other question? Okay, there's a lot of questions for this one, huh? Okay, there's two more questions. Let's try and see how much we can do. Because I am already, unfortunately, my eyes cannot stay too much longer. This is already 2 hours past midnight. It's already 2 plus AM, right? So I'm quite tired and sleepy. Unfortunately, why am I saying that? So yeah, anyway, so we have group problem solving 1, right? So let's just erase this one. Alright, group problem solving 1. Find the equivalent resultant force and couple moment acting at A. So I think I'll just show you the steps, right? Because it's quite straightforward. If you have something like this, where basically you have this force, this force, this force, and this force, right? Let's say 450, 300 Newton, 700 Newton, 1500 Newton, 30 degrees, 60 degrees, right, and all the distance 2, 4, 3, 2 meter, 4 meter, 3 meter. Anyway, so the question says what is the equivalent resultant force and couple moment acting at A. So basically, where is point A? Point A is at the end here. So the question wants what is basically FR is what, and the moment MR is what, right? So that's basically our answer. You should be knowing that from the beginning. I need FR and MR. That's the question, right? So how to get FR? So basically you resolve everything in S and Y component, you get the resultant. That's how you get it, right? So basically you can do summation of Fx, you get something. Summation of Fy, you get something. So it means, let's see, summation of Fx is negative, Fy is negative, so this one will be Fr, this one will be theta, right? So you have to provide that one. What about MR? MR is simply just the effect of all moment, right? So MR here, summation of MR, if we take clockwise as positive, so this one will be just 450 sine 60 was the distance of 2, and that's clockwise, right? Then this one another clockwise plus 306 meter, plus you have 700 cos 30 distance 4, 5, 6, 7, 8, 9. And then do not forget that we have already a couple moment there, so that's also contribute plus 1500 Newton meter. With that you can just calculate and get your answer, right? And also, if you can see the slide, it does have to show what is the theta, etc. So that's normal when you get the resultant. In 2D, you have to provide the theta, right? In 3D, it's also already in IJK, so that's understood. Okay, group problem solving 2, right? Please do try this one. The concept is exactly the same, meaning FR is just the summation of all the forces. In this case, there are several forces there, F1, F2, and F3. But also this one, it draw the 3D moment, right? So when you deal with that one in terms of resultant, also you have to add all of the moment there. However, this one, it is interesting because for those who haven't tried any before, in this one where they have the pipe and the moment, right? It's tricky to draw in whiteboard, this one. So the moment have some angle that you have to project into get the XYZ component, right? So the way you project is exactly just how you project a force, right? So you use the angle, etc. So in the end you will get XYZ component for each moment. So I'm not showing you this, please do try anyway, because this is crucial for your understanding. And please do try, and if any problem, ask me in the class or we can discuss, because we are not covering in detail this example, right? Yes. So with that, I think that's the end of the slide. So I'm rushing because my eyes cannot open anymore. So with that, hopefully you have understood chapter 4.7 and 5.8, which deal with simplification and further simplification. Make sure you are familiar with the wording also, so that you know what exactly is requested when you see the question in the midterm, for example, or the final, right? So equivalent force and couple moment system, it refers to something like this, right? Further simplification, you bring here to get the distance, right? So that's the two components. And of course, it used all the components from before, the couple moment, the moment about point, etc. So it is all in the end interlinked, right? Hopefully you have learned and understanding. So thank you very much. What am I saying? So we end the session here. Subhanakallahumma wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Wassalamu alaikum warahmatullahi wabarakatuh.